Okay, I picked out three problems from the quiz or homework assignment for this week that I think maybe will help clarify some of this stuff. I'm the really the problems that you have to do some work on. I'm gonna change the numbers just a little bit, so you still have the opportunity to do that exercise and see if you can get the answer right on your own. But I'm going to start with one that is starts off with the types of studies that we might be involved in when we're dealing with numerical variables where we want to compare means of two populations. Okay, so I'm going to read this one to start off with. In each of the following scenarios, determine if the data type are paired. P for paired data and NP for non-paired data. Okay, so now there's basically two kinds of studies that we're going to wind up with. One where we're randomizing the selection of two groups. They're random independent selections of people or subjects in each of these two groups. For instance, males in one group, females in another group. If we're comparing genders, might be a placebo group versus a drug group if we're testing the effect of a drug, and so on and so forth. Now, in certain of these studies, we might be interested in checking the effect of, say, a drug or an intervention or something like that on the same people. In other words, maybe we'll for instance, test people before they take a course and test people after they take a course. Well, that's a special situation. We're really not comparing two groups of different people the way we usually are when we randomize a study. We're actually comparing the same person against themselves before and after an intervention. For instance, if they took a training program. So, for instance, in that case, if we had two scores before and after would apply to the score that the same person had. That would be a paired type sample. So let's take a look at these, whether these different kinds of studies are paired or unpaired. Okay, let's say we want to assess the gender related salary gap by comparing salaries of randomly selected, randomly sampled men and women. Okay, so there are randomly selected men and women, and we're going to compare whether the salaries of the men are different from the salaries of the women. So one group is men, one group is women. So in that case, we know it can't be paired because since the gender is different, it's going to be two different people in each group whose salaries we're going to compare. Okay. Now, if we were comparing the salaries of women before and after they got a degree in public health, right? Well, we could see this person's salary before and this person's salary after. So it would be the same person. We can actually measure the difference between the two of them. That would be a paired sample. Compare the artery thicknesses at the beginning of a study and after 2 years of taking vitamin A for the same group of patients. There's a situation where we have a patient before, a patient we measure again 2 years later after they've been on a treatment. And in that case, it's the same patient. Instead of looking at it as two different groups, we can just look at the difference. Did the thickness, artery thickness increase? Did the artery thickness decrease? And we can deal with that as a single sample in a sense and compare it to a particular value like zero for change or no change. Assess the effectiveness of a diet regimen by comparing before and after rates of studies. Same thing there, before and after, but it's the same person. So that would be a paired sample. There's a little bit of a lag on the comments and stuff like that by the time you get them up there and by the time I actually notice them. So I see you actually working with me on this there. So I appreciate that. Okay, so let's see. Okay, so let's see. Last one was assess health inequality by comparing the infant mortality rate, the risk of baby dying between birth and 1 year of age between Iceland and Mozambique using data collected by the World Health Organization. Okay, so we have the risk of dying for infants between birth and 1 year in Iceland and risk of dying for birth to 1 year in Mozambique. Do you think that's a paired sample or a non-paired sample? Okay, I see Laura joined us now too. So what do you guys think? Are you comparing the same infants in both countries, or are you comparing two different infants? Right, different. So it's not going to be a paired sample there. Okay, it's non-paired. Good. Thank you very much, guys. Okay, good. So that's the idea then. Now let's go back now to, we know that dealing with paired samples is particularly easy for us because with paired sample, all we're really looking at is the difference. So even though we start out with two columns, before and after, we wind up with only the difference that we're analyzing. What's the difference between before and after? Is it zero? Is it negative? Is it positive? So we deal with a single sample, and we can compare that sample to the value that we would expect if there's no change, okay, which would be zero. Okay, so in other words, our null hypothesis would be there that the mean difference of all the differences, the mean difference is equal to zero. And our alternative hypothesis would be that the mean difference is not equal to zero, especially if it's a two-tailed test. We have no foreknowledge whether it should go up or down. Okay, so in that case, it's a pretty easy test for us to do. We've taken a look at that already. I'm gonna move on to something that I'm going to eventually do a problem that's similar to those things, or maybe even right now do a problem similar to that, except that I'm not going to bother with paired samples because it's relatively simple analysis. We did one in class that you can go back and take a look at on the lab video. Let's take a look at this next problem. This is actually a homework problem. I'm going to change a couple of numbers here as we go forward. Right, mu is equal to zero. Mu is not equal to zero. I might actually put mu of the differences, mu subscript difference is equal to zero, and mu subscript difference is not equal to zero. Just to make it clear that we're talking about the differences. Okay, assume that the assumptions and conditions for inference with a two sample t-test are met. In other words, that they're random and independent. Okay, so in other words, that the people that are in the two groups are selected randomly, and there's no association between the people that are selected. Okay, so it's not like all the people in one group are married to the people in the other group or something like that. Or all the people in one group are married, all the people in the other group were chosen, were not married. In other words, it's completely independent. Researchers want to compare the effectiveness of a water softener on a filter process. 90 locations were randomly divided into two groups of equal size. In other words, this idea of randomness. And we know that there's 45 locations in each group. Group A locations use a water softener and filtering process. Group B used only a water softener. At the end of 3 months, the water samples were tested at each location for softness. Okay, water softness was measured at a scale of 1 to 5, 5 being the softest, with the following results. Group A, well, now remember, is this a paired sample or a non-paired sample? Okay, it's non-paired because there's 45 in one group, 45 in the other group. It's not before and after. Had we taken all 45 and had we taken 45 and we operated all of them without a filter for 3 weeks and with a filter for 3 weeks, we'd have two columns of numbers after we tested them after each 3 weeks. And then we look at the difference between those and look at it as a paired sample. But in this case, it's 45 locations that had the filter and 45 different locations that didn't have the filter. Good. Non-paired tans. The results we got were X bar, really. X bar for group 1 is equal to 2.1. That's the hardness. And the standard deviation for group 1 was equal to 0.7. For group B, the mean was 1.7 and the standard deviation was equal to 0.4. Okay, so now using the general rule that we talked about for the standard deviation of the variance, does it look like you can assume equal variances here, or should you not assume equal variances and work with assume different variances? What do you guys think? Is one of these twice what the other one is? Is one of these standard deviation? No. So I would say we can assume equal variances. Okay, everybody okay with that? Okay, when we use SPSS, we're going to do a more rigorous analysis for whether or not we can assume equal variances. But for our purposes, when we don't have that available to us, we're going to work with it this way. Okay, now, first thing we want to do is we want to determine what level of significance we wish to work with. In other words, what's our level of alpha error? What's the maximum amount? What's the maximum probability of being wrong that if we reject the null hypothesis that we're willing to accept? Okay, well, in most cases, that's going to be equal. That's going to be equal to 5%. In other words, alpha or type 1 error is equal to 1%. Excuse me, 5%, or in other words, 0.05. So we're going to want to get a significance value or a p-value, a probability of being wrong that's less than 5%. We're going to want our p-value to be less than, p-value to be less than, didn't work out there, less than 0.0505. Oops. Okay, there we go. Okay, so now let's set up our null and our alternative hypotheses. There's really two ways we can really do this. One way is to say the mean of group 1 is equal to the mean of group 2, right? Okay, another way to say this is the mean of group 1 minus the mean of group 2 is equal to 0, right? You can see that that's really basically the same thing. A lot of statisticians prefer to use that format, okay, but they're pretty much equivalent. The other way we can describe this is the alternative hypothesis, rather. What we're trying to prove is that the means are different, that these filters work better with a filter than they do without a filter, or maybe worse. We don't know yet. Okay, the mean of group 1 does not equal the mean of group 2. Okay, so now in this case, this would be a two-sided hypothesis. Okay, does that look right to you guys? Two-sided hypothesis? Because we don't know, since it's not equal to, so we say not equal to, it's possible for mean of group 1 to us to reject the null hypothesis in two situations. One, that the mean of group 2 is much smaller than the mean of group 1, and the other is it could be that the mean of group 2 is much larger than group 1. We're not prejudging whether or not the mean is going to be greater or smaller. If we know it can't be smaller, can only be bigger, there's some constraint that would keep it from being bigger, and we wish to have an easier way, an easier path towards testing this, we can do a single sample test instead at 5%. Single sample test means that we're only looking at one end of the normal distribution. We're only looking at the higher end or the lower end, which means all 5% can be at that one end. All 5% of possible error can be at that one end, rather than 2.5% split at either end, lower and higher. If you look at that intuitively, that tells you, well, when 2.5% is at each end, you know that the two means have to be further apart from the middle, right? So if you can have 5% at one end, you know it doesn't have to be as far from the middle to get to the point where you have less than 5% chance of being wrong, or that area above which is results that you would not expect if it had the same mean. Okay, so that's really kind of why you might want to do a single tail test, because it's a less rigorous test. On the other hand, if you want to be sure you're not wrong, you might just choose to do a double-sided test anyway, even if you had the opportunity to use a single-sided test. Okay, so now we're going to do our calculation. We've decided that in this particular case, we have equal variances. Now, I'm going to change these numbers. I'm going to change this to 2.3 and 1.4. Okay, and we're going to calculate what our, actually I'm going to maybe I'll change it a little bit differently. 1.4 and 2.0, let's say. Okay, let's test our hypothesis now. Let's see what we have to do our calculation. Well, if you guys remember, we made up a sheet. By the way, I uploaded that to Blackboard tonight, so you should be able to get to it. let me just get to the right folder here. We have a, let's see, which one is it? I put together a template for us to use, okay, where we can look at the different kinds of tests that we might have. Okay, so here, compare the means of two populations, right? If we assume that standard deviations are equal, well, that's our case in this case, right? We decided that standard deviations are equal, and we can go ahead and use that. Alternatively, if we decide the standard deviations are not assumed to be equal, well, then we would use a different method. Okay, we'd use this method and these formulas. Okay, and if we were working with proportions, we would wind up using these formulas. Okay, so I think this version of it, the spring 2016, a little bit clearer, a little bit easier to use than the previous one. But let's leave this open and see what we need now. Well, first thing we got to do, we already got our null hypothesis, and now we have to calculate our t-value. You know, t-value is going to be equal to the difference of the two means divided by the standard error. And this is the way we're going to calculate our standard error. Now, did I make a mistake here? Do I have this right? I think I got it right, right? Oh, no, I got the wrong one. It's up here. Here we go. Since we're assuming that the standard deviations are equal, okay, or we think that they're equal, we're going to be able to pool those standard deviations. In other words, take advantage of the fact that we can base the standard deviation on 90, a sample of size 90 rather than a sample of size 45, which each group was, and that gives us a better estimate of what the standard deviation really is for the population. So first thing we're going to do is we're going to calculate a pooled standard deviation. Okay, so let's see what I'm going to open up Excel and do it in Excel. Okay. I'm not sure why it's asking me. Oh, I know. Oh, that's some work we were working on before. Let me close that. Open a new one. And I'm going to size this up so we can see it. Okay, it's a little bit easier to see there. Okay, so I'm going to accumulate all this data here. First, I'm going to type x bar 1, x bar 2. Okay, then I'm going to say standard deviation 1 and standard deviation 2. Okay, and this was equal to, let's see if I can't find it again. Here we go. Let me do it this way. Okay, standard deviation 1 was 0.7. Standard deviation 2 was 0.4. Okay, and now I want to calculate my pooled standard deviations. How do I calculate my pooled standard deviation? And then if we have that, I can get this out of the way, and we can go look at this. Okay, let me get the full screen over here so I can work on this. Okay, so our pooled standard deviation, what are the things we're going to have to determine here? First, these n1 minus 1, well, that's going to be 45, correct? So n is 45, so that's going to be 44, right? That's equal to 44 times S1 squared. S1 is 0.7 times, again, squared is 0.7. So this first value is 44 times 0.7 squared, 0.7 times itself. The second value on top is going to be 44 times S2 squared, where it's going to be equal to 44 times 0.4 times 0.4. It's going to be equal to 7.04. Well, now we're going to want to add those two together. So I'm going to say that's equal to the sum of these two values. Okay, and that's my numerator. That's the top part of my equation. The bottom part of my equation is going to be equal to n1 plus n2 minus 2, 45 and 45. 90 minus 2 is 88. Okay, so now my pooled standard deviation is going to be equal to, I'm going to put that over here, SP is going to be equal to the square root of the numerator divided by the denominator. Now, if you're adventurous, you could do this obviously all in one cell, but I just thought I'd do it step by step here, so maybe minimize my chance of getting this wrong a little bit. Okay, so the pooled standard deviation that I get is equal to 0.57. I'm hoping that's right. It does look right because it's kind of in between these two values. In fact, I'll bet you it's almost exactly in the middle because the two sample sizes are the same size. Okay, it's kind of like a weighted average of the two of them. If the sample size had been bigger for S2, well, then it would have been closer to point. We would have expected it to be closer to 0.4 than to 0.7. But that's neither here nor there. Okay, so now let's calculate what our t-value is. Our t-value is equal to the difference in the two means. Okay, whoops, actually, I should have written that up here, right? Okay, which is going to be, what did I say? I changed those numbers, didn't I? Where did I put it? Should have remembered to write them down. They were 2 and 1.4. 2 and 1.4. Okay, so the t-value is going to be equal to, and let me get the formula up here so you can watch it at the same time. T-value is going to be equal to, I'm going to put it in parentheses, I'll do it in one cell, is going to be equal to 2 minus 1.4, close parentheses, divided by the pooled standard deviation, which is this number right here, times the square root of 1 over n1, which is 1 over 45, plus 1 over 45 and 2. That's 2 over 45. 2 divided by 45. Okay, now I got to put this all in parentheses so that it handles that denominator correctly, I think. Let's see. Okay, so it's going to find square root of this. It's going to multiply by this pooled standard deviation, and it's going to divide that into the difference of the means. So I think I got this right. I'm going to hit enter. And it looks like my t-score is 4.99. Well, right off the bat, that's a pretty high number, right? But if I want to check it, I have to see, I'm going to go to the t-table. Okay, here's our t-table. And we know that since we're working with a value of an alpha of 0.05, it's a 95% confidence interval. In each tail, it's 0.025 for two-sided. So we're looking in this, we're looking in this column right here. Okay, so for an alpha error of 0.05, same as a confidence level of 95%. So I'm going to slide down here, and you'll notice that the higher you get in degrees of freedom, the smaller the critical t-value. In other words, this t-value represents the t-value you have to exceed in order for the p-value to be less than 0.05. The probability of being wrong if you're rejecting the null hypothesis being less than 0.05. So if my sample size was 100, I would have to exceed a t-value of 1.98. If my sample size was 10, if my degrees of freedom were 10, I would have to exceed a value of 2.2. If my degrees of freedom was only 4, I'd have to exceed 2.7, or 3, 3.1, or 2, 4.3, and so on and so forth, right? So what is our degrees of freedom for this example? When we're working with equals, when we're assuming equal variances or equal standard deviations, the degrees of freedom is n1 plus n2. 45 plus 45 minus 2 is 88. So it's going to be pretty close to 80 or 90. So the number we have to exceed, I'm going to use 90, is 1.99. Since we got a t-value of 4.99, we can reject the null hypothesis because we know that we've exceeded the critical value of t that we need to have a p-value less than 0.05. I see there's a question there. I'm not ignoring you. Just trying to finish up. Okay. Can you explain how you picked that a bit more? You mean how I picked the t-value or how I chose which column to use? Laura. Which column? Okay. Which column do I want to use? Okay. So now the idea that we're willing to have up to 5% error, right? Well, that kind of goes along with the fact that we want a confidence level of that. We want to be 95% certain that we're right. So in other words, we're willing to be 5%. We're willing to accept a 5% chance of being wrong. If my alpha is equal to 0.01, that would be equivalent to saying I want to be 99% sure that I'm right when I reject the null hypothesis, or I'm only willing to accept a 1% chance of being wrong. So an alpha error of 1% corresponds to a confidence level of 99%, and a confidence level of a alpha error of 5% is a confidence level of 95%. And also, if I was willing to accept 10% chance of being wrong, alpha is equal to 10%, then my confidence interval or my confidence level would be 90%. Okay, so and the degrees of freedom, the degrees of freedom is typically the sample size minus one. In this case, we have two groups. So when we're using equal variances, the sample size determines how likely it is that how big a difference between the means that you need in order to reject your null hypothesis. Okay, remember the t-test and the z-test, that's really a measure of the number of standard deviations apart that your x bar 1 and your x bar 2 are. So if I have a small sample size, they have to be further apart. That t-score has to be bigger number. Okay, if I have a big sample, that t-score can be smaller. And the smallest it can be is 1.96 for the normal distribution. In other words, when we know what the true standard deviation is, we would use 1.96. So that's why I'm using the middle column for an alpha error of 5%. And remember, this I'm calling this the critical value because that's the size of t that we have to exceed in order to reject the null hypothesis. Okay, does that help? Okay, that's just an okay. All right, that's just an okay, but that's okay. You don't have to understand this completely the first or second time that you see it, because some of these concepts are, especially if you haven't been exposed to this too much before, some of these concepts can be a little bit difficult to grasp at first. But as you do some repetition, as you do the problems and the homework, as you go maybe through some of the examples in the lab exercise that we didn't complete in class and stuff like that, and even if you just watch a couple of YouTube videos on t-test and the t-table and stuff like that, it'll help to cement your understanding of it. And if you really want to remember how to do it, just teach it for 15 years, and it'll be burned into your brain like nothing you've ever known. So at any rate, let's see. All right, so let's see. I like to tell students, like at the end of the semester when they all graduate and stuff like that, that I'm the only one in the class that gets left behind. So compare the t-value. So let's see. So that's the situation. Now notice we didn't really get a p-value there, right? Since we had the t-table, all we knew was that we could reject the null hypothesis that p was less than 0.05. You can actually game the system a little bit, and see, it's also smaller than the critical value size, 80 degrees of freedom. It's still smaller than this number, so we could have rejected the null hypothesis even if we were at the level of 98% or an alpha of 0.002, right? Really small alpha. We could actually see which one it's between to get an idea of where the p-value is, where the probability of being wrong is, or what the areas and the tails are, how far apart those means are. Right, we could actually game it a little bit, but we never get an exact number from this. When we use SPSS, it actually calculates an exact number for the t-value. Now, I just wanted to point out that had we said that the variances were not equal, that they were unequal, we'd have to use a different set of formulas. Okay, we'd use this formula. T is equal to the difference in the means. Again, you set up your null hypothesis, and you determine your level of confidence, like 0.05 usually. Okay, now standard deviations and means for both samples, if you know them, you say x bar minus x bar 2 over the square root of standard deviation 1 squared over the sample size 1 added to standard deviation squared of sample 2 over the sample size of 2. And you can calculate from right from here what your t-score is. Now, in order to decide whether you can reject a null hypothesis, you have to compare your t-score that you find here to the critical value of t. So now, in order to find the critical value of t, you need the degrees of freedom. Unfortunately, when you're working with unequal variances, you have a rather complicated formula. Instead of just adding them together and subtracting one, you have a rather complicated formula for determining what the degrees of freedom are equal to. You'd have to actually work this formula out to calculate it. And it could be an odd number like 52.3 or 71.7, right? So this is a little bit intimidating. If you don't want to do this, you could take a conservative approach, and instead of bothering with this, you could say to yourself, the degrees of freedom is equal to the smaller sample size, whichever one that is. In our example, they were both the same, 45. So you take 45 and subtract one and use and assume that the degrees of freedom is equal to 41. Okay. Again, usually subtract one from the sample size for the degrees of freedom. In the previous example, we had two samples, 45 each. We added them together, subtracted two. Okay, for one for each sample. Okay, so that's a difference in the way that you would handle the calculation if you assume the standard deviations to be equal, or if you assume the standard deviations to be not equal. And then again, with proportions, we're dealing with another factor where we are again, since the rules for the proportions usually means that we're dealing with a sample size that's pretty big, right, for proportions. Well, then we're dealing again with working with a pooled standard deviation. This P1 is the proportion for one group, like 10% diabetics in one group, 15% diabetics in the other group. These are the sample sizes. So your pooled standard deviation. And then when you calculate your z-score, you use z here because we're working generally with large samples. You calculate your z-score. You look at the difference in the proportions for the two populations, population 1, population 2, over, now this P represents the pooled standard, the pooled proportion, okay, whatever that turned out to be, where these two represent the proportion of group 1 and the proportion in group 2. Okay, so it's the same kind of calculation, except you wind up doing it a little bit differently. We don't have to worry about the degrees of freedom here because our result is a z-score. So we can just go to Excel or the z-table to figure out what the p-value is. Okay, now if you get a p-value for the z-score, let's say you get a value, let's say it turns out to be negative 2.01. Well, that means negative 2.01 is two standard deviations to the left. The area that's left to the left of that, we know if it was 1.96 standard deviations to the left of the mean, in other words, a z-score of negative 1.96, there would be 2.5% left on the left-hand side, because that's, our two standard deviations left and right. Okay, but with 2.1, 2.01 or 2.1, there'd be less than 2.5%. Maybe there'd be 2%, right? So if there's 2% on the left, remember, the result here happened to be a result that turned out negative for a z-score. Well, before we did this, we didn't know that it was going to turn out negative, so we have to account for the fact it could have been on the other side as well. So what we do is we take that area, that 0.02, we double it so that we account for the upper end also when we're doing a two-tailed test. Okay, so that's the way we deal with that. If we're doing a one-tailed test, we don't worry about that. All of it's on one side. Okay, so at any rate, so that's how we deal with these. Now I want to do an example. I'm sorry I didn't start this program up before I started talking. I want to do a quick example that involves SPSS. And the idea of doing a quick example went out the window now because we know it takes a long time on these machines to start that up. Okay, and let me see if we have a version of this problem here. Okay, in the assignment, that problem uses the North Carolina birth data, okay, to test the hypotheses at a alpha is equal to 0.05. Okay, that the average mother's age is different between mothers who, the average mother's age is significantly different between mothers who smoked during pregnancy and mothers who did not smoke during pregnancy. Okay, is that going to be a paired sample or an unpaired sample? Okay, we're going to have two groups, right? One is mothers who smoked, and the other is mothers who did not smoke. So is that a paired sample or an unpaired sample? Not paired, right? We get that? It's not paired because the two groups, one group is mothers that smoked, the other group is mothers that didn't smoke. So they're not paired. They're two different groups of people, right? If I had told you that we wanted to measure the weights of mothers who smoked during pregnancy in 1999, and then go back and check their weights again in 2000, right? Well, the problem there is that, gee, it's the same person, isn't it? You're measuring them in 1999 and in 2000. In that case, it would be a paired sample. The two numbers that you're working with would apply to the same person. Okay, in this case, the numbers that you're working with, the age of the mothers, group one is the mothers who didn't smoke, group two is mothers who did smoke, two different women in two groups, in the two groups of numbers. Okay, so that's a non-paired sample. Okay, good. So if this eventually opens up sometime tonight, we'll give this a try. Let me get this out of the way. In the meantime, I'll clean up things in the background here. Okay, come on. Start her up. Okay, well, I'm also going to, you know what, while we're working on this, I'll say, okay, what's our null hypothesis here? And what's our alternative hypothesis? Okay, on null hypothesis, you could look at it two ways, right? That mu, the mean age for smokers, mu for smokers, is equal to the mean for non-smokers. Okay, and that's age. Okay, another way to do that would be to say the mean for smokers minus the mean for non-smokers is equal to 0. Okay, well, how about the alternative hypothesis? In that case, the mean for smokers does not equal the mean for non-smokers. Oops, mu for non-smokers. Or if you described it the other way we did it, would mean for smokers does not equal the mean for non-smokers. Mean for smokers minus the mean for non-smokers does not equal 0. Okay, is that a one-sided test or a two-sided test? That's right, two-sided test. Yeah, good. Okay, now a hint. If you see something like, if I were going to call this a one-sided test, for instance, if I thought that if I wanted to prove that non-smokers that smokers were older than non-smokers, right? I'd start with the assumption that that the mean for smokers, right, is that they're younger or the same age as the mean for non-smokers. Okay, younger, less than, or equal to the mean for non-smokers. And I'd make my alternative hypothesis. The mean for smokers is greater than the mean for non-smokers. What does that give me the opportunity? That gives me the opportunity to say, if I can reject this as being true, that then I've proved that non-smokers are older than smokers are older than non-smokers. That would be a one-sided test exactly. Another hint: never ever put the equal sign in the alternative hypothesis. The equal sign is always in the null hypothesis. Okay, the alternative hypothesis never has the equal sign in. Okay, so just so if you wind up working with it, you know that that's the case. Okay, equal sign. The equal sign in either less than or greater than is always in the null hypothesis. And what you want to prove, what you want your final result to be, you want to be able to reject this as a possibility. So that leaves the alternative. So you can accept the alternative, which is what you've got down here. Let's see if we're having any luck with SPSS. In the meantime, I'm going to go back to here and I'm going to double click the data file as well. Maybe that'll speed things up a little. We'll open eventually, I know that. Can't imagine what it possibly could be doing when it takes all that amount of time to open. Okay, in the meantime, how are you guys doing? Are you guys okay with this up to this point? Because I know that as we get into the second half of the semester, that things really accelerate quite a bit. We start working with a lot of real statistics, a lot of real life scenarios where you might be using statistics. And it can be a little bit, the second part of the semester can be a little bit challenging because of that. So I understand that, like, as we throw these tests out, we progress very quickly from confidence intervals to one-sided t-tests to two-sided t-tests. And we're going to be moving on to chi-square tests, and we're going to be moving on to analysis of variance and regression, and so on and so forth. So things go very quickly. Fortunately, a lot of those elements of the course are things where you actually apply them. So you can brush past a little bit of the theory. You need to know some, so you know what you're doing, but you can really concentrate on applying those, understanding what kind of data to apply those tests to, and how to operate them. A lot of times we'll be working with software too, as we move forward, even more often than we did before. So some of it will be a little bit easier in some cases. So if I were going to set this up for the analysis we just looked at, well, one of these variables represents the weights of the mothers. This is the amount of weight gained. Does it have their regular weight? Yeah, I would say probably it's just talking. I think the problem is probably talking about the amount of weight that they gained. So gained is a variable name for, and in fact, you can see it in the label. You can see that that's weight gain during pregnancy. Okay, so we're interested in that. And we're also interested in whether they're smokers or not. So what variable is that? Well, here's a variable smoke and smoke during pregnancy. Yeah, that's what we're after. Now, what numbers represent smoking? I'm going to click into the values column here, and 0 represents mothers who did not smoke. 1 represents mothers who did smoke. So I'm going to go in here and, whoops, cancel. Okay, I'm going to go to data view just for the hell of it. And I'm going to say, let's analyze this now. And let's compare the means of two groups. They're independent samples, right? It's not a paired sample. They're independent samples. Okay, and the variable that we're testing is the amount of weight gained. Okay, we want to know the mean weight gained for two groups. And we're going to put those groups, we're going to put the grouping variable, how we want to split that up down here. And that's going to be by whether or not they smoked during pregnancy. So our grouping variable is whether or not they smoked during pregnancy. It's going to create two groups, group 1, group 0, and group 1, right? 0 was smokers, group 1 was non-smokers. It might be the other way around, I don't remember. But we're going to look at the weight gain, the average weight gain for each of those two groups. That's how we fill these two boxes. So I'm going to go here to options and just check. Oh, look, confidence interval percentage is 95. We know our alpha error, we want our alpha error to be 0.05. That was stated in the problem. So we're going to leave that 95. Had we said we only want to tolerate 1% chance of being wrong if we reject the null hypothesis, I would have changed this to 99. Okay, just like I would work with the t-table as we were discussing before. So now I'm going to say, okay, now it asks me to define the groups. What that really means is it wants to know what are the numbers that represent these two groups. And the reason why it's doing that is in case there's other categories. If this were ethnicity and 0 were one ethnic group and 1 were another and 2 were another and 3 were another, if we're only comparing 2 of them, it would want to know what those numbers are. In other words, am I comparing 2 to 4 or 1 to 3? And so on and so forth. In this case, it's only two groups. You would think it would be smart enough to figure that out, but unfortunately, it asks you to fill this in. So group 1 is 0, group 2 is equal to 1. If you get this wrong, like for instance, if I didn't look and I put 1 and 2 in here, it just wouldn't work. It would give you an error and tell you something's wrong. So you got to go back and look at what you did. Okay, so I'm going to click continue. Okay, and now my OK button is available for me to finish the analysis. I'm going to click OK. Come on, there we go. Now the output window will open up, and in the output window we'll have our results. So what do we have here? Mother did not smoke during pregnancy. The average amount of weight that was gained by mothers who didn't smoke during pregnancy is 30 pounds. The average mothers who did smoke during pregnancy was 30.2 pounds. Not much of a difference, is there? Well, it's hard to tell whether these two are different enough to reject our null hypothesis until we do our t-test. Okay, so we want to see they're pretty close, but these are really big samples. So maybe we have enough evidence that even though it was only half a pound, maybe we have enough evidence to say that they were different enough to say that those two populations had different weight gains. Okay, so let's look at the bottom. First thing we look at the bottom is we get two results. The SPSS has worked the problem out for us. It's calculated t-test, degrees of freedom, significance. The significance equals the p-value, or probability of being wrong if you reject the null hypothesis. It does it for equal variances, and it does it for unequal variances. It actually does the calculation for both situations. Okay, so let me take a look at this now. First thing I want to look at is which one of these lines, the top line or the bottom one, should I use? Well, I look at this as if, remember again, much of statistics, we're starting with the null hypothesis that things are equal, there's no difference. Okay, our null hypothesis here is that there's equal variances. Our alternative hypothesis is that the variances are different. Okay, the bottom line. Okay, so if I look at my statistic, my test statistic, Levine's test for quality of variances, right? My test statistic comes out to be 6. My significance for that test, and these 4 boxes here represent only the test for variances, nothing else. Okay, comes out to be 0.012. Well, since that is less than 0.05, my null hypothesis is equal variances. Since that is less than 0.05, I can reject my null hypothesis and say and use my alternative hypothesis and accept my alternative hypothesis. Equal variance is not assumed. So I'm going to use the bottom row here to do my calculation. I know that there was a issue with the PowerPoint, and I think some other stuff that suggested that it was the other way around, but we'll get that straightened out by our next meeting. Okay, so you should use the bottom line. Okay, so let's see what our t-score is. Our t-score is 0.294. Well, that's not very good, is it? That's a small number. It's not even 1. So it's only a third of a standard deviation apart, these two means. That's not very promising. Well, and our degrees of freedom are 139.666. Remember that when we did unequal variances, it uses that complicated formula to calculate the degrees of freedom. That's why we got such an odd number. Okay, and what's our p-value? What's our significance, our probability of being wrong if we reject the null hypothesis? P is 0.769. Well, then that's two-sided, so it's already been doubled. Okay, 0.769. I'll compare that to what I want it to be. I want it to be less than 0.05. Well, since it's not less than 0.05, what do I do? What is my conclusion in this case with regard to the hypotheses? I'll ask you guys, and we'll say good night. What do you think? Do we reject the null hypothesis? No. Okay. We fail to reject the null hypothesis. Do we accept the alternative hypothesis? What do you think about do we accept the alternative hypothesis? Well, we failed to reject the null hypothesis, so we can't reject the null we can't accept the alternative hypothesis. Good work, Laura. And now had we had a number here less than 0.05, right? We would have rejected the null hypothesis, and we would have rejected the null hypothesis, and we would have accepted the alternative hypothesis. Now, we never say in this case where we don't reject the null hypothesis, we don't say we accept the alternative, we accept the null hypothesis.